Okay, cool. We'll get started then. I think everyone's here for the specific reason of the presentation on self-driving cars, so I won't give it too much intro. Um, I'll be talking about the machine learning that's inside of self-driving cars. Yeah, yeah. I'm recording it locally. I can also record it on Zoom, but I'm not sure if that's exactly going to lay out how I expect. So I wanted to just take control of it with my own recording software. Um, and so just a little bit about me. A lot of you know me because you see me every week. But then for those of you who don't, my background is I have a degree in business entrepreneurship. I went to school, and my hope was to make this big, massive Facebook scale business. And then I got to the end of the program, and I realized I didn't have the money to start a company of that size. I didn't have the skills to make any software products. I didn't have any of the tools really necessary to do that. And I didn't really think that the route of going and looking for venture capital and trying to kind of do all of that without any actual skills was going to work out for me. So what I ended up doing is um, I was at home and I just started picking up skills on my own. So I taught myself Python, I taught myself data science, I picked up Kaggle, and then I started competing there in the hopes that I could build up my credentials through that and then be able to get a job in data science because I thought it was a really interesting field. Um, and so um, in that process, I was doing Kaggle competitions. I was doing really poorly, and then I decided to go get external help and go talk to other people. And so I went to this local machine learning meetup, and I met this guy Alex, and he was an ex Microsoft employee who was looking to also work on competitions and change his career. And so we worked on the toxic comment competition. And so we got heavily invested in it because both of us were unemployed at the time. So it was just our full time thing, basically devoting our life to learning NLP and figuring out all of the challenges there. And we ended up getting third. And so that ended up bringing me to be able to get a job and continue in my career. And I had such a good experience with that, I decided um, once the previous meetup kind of fell apart, I decided to continue it with the San Diego machine learning group that we have today. Um, and so just this picture off to the side is um, all of my accolades from the Kaggle stuff that I keep doing. Um, and so on to the self-driving cars. I split this talk up into two different sections. So one of them is kind of the um, business and the background of everything, and then the second portion will be about the actual technology that goes into these systems. And so the first thing that I want to discuss is the five different levels of self-driving cars and what a self-driving car actually is. So for a long time, everyone's had what's now considered level zero, which is no automation, nothing special in there. And a lot of cars at this point are starting to transition to level one and level two. And so what that means is they have some form of assistant. So you've probably seen cars as early as possibly 2010 that might have some form of adaptive cruise control. So if you have normal cruise control, it will just keep you at 75 miles per hour on the highway or something like that. But if you have adaptive cruise control, then it will also adjust your speed if a car's in front of you, or if you have open road, it'll speed up. Um, and it can also manage certain things in terms of warnings and automatic emergency braking and stuff like that. If it detects a car that is really close to you, then it can um, do some minor actions in order to avoid collisions. Um, and so that's level one, and level two is partial automation, and that's what a lot of people consider um, Tesla to be, and all of the various different systems at this point, which is um, partial automation, where some things are aided or sometimes replaced versus having a driver actually take all the actions. So in the Tesla autopilot, it can navigate the roads, it can do lane changes, it can keep a safe following distance, it can do a whole slew of things. So that stuff is kind of the lane keep assisting and the advanced adaptive cruise control, and potentially also dealing with intersections and stuff like that, which is its whole own problem. And then there's level 3, which is building on top of that, and the big distinction between level 2 and level 3 is confident enough that in certain points it can be the primary controller. So level 2 is just a sort of crutch that can help the driver, and level 3 can actually replace the driver in some aspects. And this is a big leap because that means that the manufacturer is actually confident enough to take some liability. And so if the car is actually in control, then they are the owners of any damage or something that happens there. Um, and so the level 3 is just, for example, let's say you have a highway that has been heavily trafficked by an autonomous vehicle, and they've done it 1,000+ times, and they say, okay, we know that it can safely traverse this single road. Then it would be something that they're confident enough to say, okay, we can allow this car to drive on this strip of road. But it's not necessarily saying that it can drive every strip of road. It can't handle all scenarios, but it can at least take full control during some pieces. Um, and then level 4 is high automation, and that is what a lot of people are aiming at, which is trying to get it to handle basically all scenarios, and the car is directly in charge of what's happening. And in some tiny edge cases, a driver might actually intervene and be needed, but for the most part, the car is in control. And then level 5 is full automation, which is saying basically there's no human ever needed. It will be able to do exactly the same function as if a human was in the car automatically. It can go anywhere. It can do dirt roads. It can do whatever. It can reason well enough that a human isn't necessary. Um, I see something in the chat. If you guys ever want to ask a question, feel free to plug stuff in there. Um, yeah, so each level is adding. Um, I don't remember if I put this slide in or not. I had another chart that I was going to show where the distinctions are kind of subtle at certain points. So some people put different tasks at different levels. But the big distinction is between level 2 and level 3 and beyond, which is basically where the auto manufacturers or the self-driving providers end up taking more responsibility. Um, yeah, I'm not sure exactly the heart of the question. Maybe if you can rephrase that, I could add more context to that. Um, and so one of the important things to understand is, why are self-driving cars valuable? And there's a lot of different aspects. They're just exceptionally cool. Um, but the actual tangible benefits are the convenience. So there's a whole bunch of drivers in the US and worldwide, and they spend a whole bunch of time behind cars. Over 12 days is the recorded number that I found. And if you could win back 12 days of time from millions of people, that could be massive for the economy and for people's quality of life. And then on top of that, there's large safety aspects. So it really depends on what source you look at, but it's reported that um, the number of accidents on the road can range from 20 to 50% are human fault. Um, and so if we could eliminate 50% of car crashes, and it's the eighth leading cause of death, we could massively reduce the number of people who are dying while we're driving around. And so the hope is to one day have a system that is more reliable than a human. They don't drunk drive, they don't lose focus, they don't make poor decisions, they don't drive recklessly, and that could save many lives. So it's something that could be very significant and change society and the way that we structure things. Um, and then the environmental impact, there's a huge cost to every car being made. There's tons of steel and rubber and plastic and gasoline and electricity that's consumed and all of this stuff. And there was a United Nations environmental program report that said that vehicle manufacturing is more damaging to the environment than basically any other field. Um, and we make all of these cars, and then, especially right now with everyone um, stuck at home with COVID, we've got these expensive to manufacture things that are just sitting and doing nothing. And so, in an alternate world where we have self driving cars, ownership might no longer be necessary, and we don't have to make so many cars, and they can be shared. And so, we could greatly reduce the amount of environmental impact that we have just from our transportation. And on top of that, we can optimize our self-driving systems to, in one aspect, since we're reducing number of crashes, we'll reduce the number of cars that are totaled, which also um, helps the environment in that way because we're not wasting the materials. But you can also optimize your machine learning system in order to increase your miles per gallon. You can also make it reduce emissions because humans are not necessarily perfect in terms of driving efficiency. They might go too quick off the line. They might brake more frequently than they need to. There's a whole bunch of things that can be optimized there in order to reduce the environmental impact, both on the manufacturing side with ride sharing and also on the side of increasing efficiency and reducing emissions. And then they're also valuable because there's a lot of companies who can make a whole ton of money off of them. So if Tesla is able to be one of the first companies to get self-driving cars to the market, all other cars will be obsolete and their cars will be worth tons and tons of money. And similar things for Uber and Lyft and various other companies that are trying to provide some service that will just greatly increase the value of cars just by putting a little bit of tech in them. And so there's a whole ton of players in this space, and this is a slide from Comet Labs, and this is just showing all of the different stuff that people are working in the transportation field, in mapping, in sensors, in autonomous driving, in um, trucking. There's just so many different fields that people are um, focusing on this, and it's just a very hot area right now. And so the first three things that I wanted to focus on, there's so many different um, companies working on this, but I pulled these three out partially because they're the ones that I'm most familiar with, but partially because they're taking very different approaches um, to achieving these goals. And so the first one is comma.ai. They're actually a local San Diego company now. They moved here from the Bay Area, and they're working on building level 2 self-driving capability and making a kit that is essentially retrofitting current cars to do level 2 self-driving. And then there's Tesla. I believe most of you are probably familiar with them. They've got their Model 3 and Model S and Model X, and they're these phenomenal cars that have all of these sensors in them, and they are promising down the road level 4 self-driving capability. And then there's Waymo, which is even further on that spectrum, where they have spun off of Google, so their own company now, and they are trying to build a level 4 self-driving car totally from the ground up. So the Tesla is just a regular consumer car that you can get for 35 to 100K, and the Waymo is just purely aiming to solve the problem first. So they have $2 billion plus of money, and they're essentially just saying, can we build a car that does this? Because that would be exceptionally valuable. And the Tesla is going from kind of the opposite approach of let's get a consumer car and try to amp it up to get to that point. So looking at COMMAAI first, like I said, they're a San Diego company. They are an open source project, so if you want to look at everything they're doing, it's all on GitHub, and you can check out the specs to their hardware, the specs to their software. You can people have made various different forks, so if people want to do some slightly custom feature, they can just make a fork, push that to their drive, or push that to their device, and then they're able to um, do new custom features, and then potentially, if it's something that's good enough, it will get merged back into the main product. And so the gist of this device, I actually have one right here. I actually really enjoy it, showing that off. Um, it's I would liken it sort of to a TomTom or a Garmin of the past. And so the way it works is you have this device. It's essentially a phone in a 3D printed case, and it plugs into your car with an OBD2 port, and then it is able to control your car. They call it drive-by-wire, which is essentially they can control the steering and the gas and the braking. Is the data open source? No. So the data is not open source, but the trained models are open source. And that's something that I've looked at a little bit. Um, they have them up and available, and they're in the sort of special Qualcomm quantized format. And you can convert that back to TensorFlow, and then it's inspect the graph and look at the weights and all of that stuff, and you can continue training it if you want. But that is a little bit of a hassle to go from the Qualcomm format. They've specifically converted it to that so that it works on the phone hardware with the Qualcomm chip that's inside. Um, and so the amazing thing about this device is it's just a normal $600,000 device, and you plug it into your car, and then it can do these awesome things. It can keep you in the lane. It can keep you safe distance from the person in front of you, and maintain speed and all of that stuff. And all it's using is the front-facing camera and the rear-facing camera of the phone, and then it's also interacting with the built-in radar of the car. The face camera is monitoring the driver or looking behind the vehicle. So the front-facing camera, I'll go to the next slide. So the outward-facing camera, the one that's looking forward, that's the higher resolution camera, is looking at the road, and it's trying to detect the lane lines and determine what angle to turn the steering wheel and whether to apply gas and brake. Is there a car in front of you? Is there an obstruction of some sort? And then the front-facing camera, the one that people typically use for selfies, they've actually replaced in the newer models with an infrared camera, and that is used in order to look inside the cabin of the car, not necessarily behind the car. And the goal of that is just to monitor the driver and make sure they're paying attention. It's not necessarily to look at the cars behind them. And so that's one of the key features, though, is many accidents are they occur because people lose focus, and these autonomous systems at this point are not perfect. So the expectation is that you continue paying attention even while the system is assisting you. And so that's some of the issues that have come up with Tesla and Uber and the various other systems that have crashed. Typically, it has been the system making an error, but on top of that, it's been someone not paying attention. And so, what Comma is trying to do is make sure that they acknowledge our system is not 100%. It's not going to always make the right decision, but hopefully, we can at least make sure that the driver is aware, and we can give them warnings. Hey, this is an uncertain scenario. We need you to take over. And part of that is making sure that the driver is looking where they're going, because the system itself is not always going to be able to tell what a tricky scenario is, or notice a car merging in the way. Fubu's got a good point there. I wasn't aware they released a data set. A lot of the companies have been releasing some limited data sets. I wonder what that is. I'm not sure if that'll be just raw video. Do you know, Vibu? Mm-hmm. Cool, cool. Thanks for that. Um, and so this is largely limited to highway driving. So I used it a whole ton when I was working for a different company, and I would drive up to San Clemente all the time. So that's about a 40-50 minute drive depending on traffic. And it, on the way there, it's probably 80% highway for me. And so I could just turn the system on and it would deal with the steering and the gas and the brake. And it really removed any stress from my commute because I didn't have to really think a whole lot. I'm just monitoring it, making sure it's keeping me in the lane. My hands are on the wheel, but I'm not really driving. It's just guiding me along. And I really can't stress how much it reduced um, the fatigue of driving. It really just made it significantly better to be able to just kind of sit there and watch rather than actively making small adjustments to keep myself in the lane, and um, turning on the gas a little bit and then the brake a little bit when someone slows down in front of you and all of that stuff. It just really removed a lot of the stress there. And so their tagline is making driving chill, basically. And I think that they have done a pretty good job with that. But it is significantly more limited than a lot of the other systems, so it can't necessarily take you around a corner. It can't detect a stop sign. It can't do anything too fancy in that regard. But given the hardware, that's about all you can do safely. You can't necessarily um, make it do more complex things because it's only given a limited amount of context. And so the next one we'll look at is Tesla, and I would pin them as the leader in terms of the actual self-driving cars on the road. And I put self-driving cars in quotes because that definition is kind of loose. That's kind of what people think of in terms of self-driving cars is level 5, and at this point they don't have level 5. Um, but they do have very, very good level 2, almost level 3. And so, in order to do that, they've fit their car with 8 cameras, 12 ultrasonic sensors, an exceptionally powerful onboard computer. They've designed custom chips in order to be able to handle all of that signal. Um, and that's in contrast to the previous system where we're just looking at a standard phone. It's not any special hardware, and they've specifically optimized their hardware for their specific task. So it's an entirely different ballgame. They're just dealing with so much more data and so much more throughput. So with that additional information, that additional processing power, they're able to do even better steering and braking and lane changing and understanding intersections and being able to reason about everything that's around them. So if you've seen their dashboard before, you can see that they are aware that there's a car in the right front of them and behind them, and in all directions they have strong awareness. And down the road, they have promises of full self-driving. So that's one of the features that they've been selling for a small premium. And then Waymo, which is another alternate approach. And the big differentiator here is that they add LiDAR and a few other custom sensors. And This is a big deal because LiDAR is actually exceptionally expensive, and multiple other companies have come out and basically said LiDAR is just a crutch. What LiDAR does is it allows you to measure the distance to basically everything around you. And I'll talk about this more later, but there's some debate on LiDAR versus camera versus ultrasonic and radar. People have different opinions on what sensors are actually necessary in order to produce a self-driving system. And at this point, Waymo has a bit of an advantage because they have this expensive sensor on their car that tells them a whole bunch of stuff that you can't currently get with just cameras or radar or ultrasonic. Um, so now we'll get into the second portion, which is actually looking at the machine learning that goes into self-driving cars. And so I've split this up into looking at um, the several different subsystems. I only listed three, but some people break them down even further than I do. Um, and so I split it into perception, planning, and control. And so perception is just you need to understand what's around you in order to do any action. And planning is, okay, you understand the world. How are you going to move within that world in order to do anything? And then controls is how do you actually take that action to push out your plan. Do the ultrasonic sensors emit a signature unique to the car so that they can dismiss all ultrasonic echo emitted from other self-driving cars? That was actually something when I was reading up on. That is somewhat a problem in most of the sensors. So you can have some issues with LiDAR and radar in that regard as well. But I think it is a big problem with ultrasonic. But at least with the current landscape, ultrasonic has relatively low range. Um, I don't remember the exact rating, but I don't think that it's the biggest issue. You won't necessarily have a problem um, with dozens of cars around you. I don't think. That doesn't seem to be a problem that people are trying to address. Is there debate about whether a self-driving car should show occupants what it sees and knows, or the other side, cars should just drive, not over-inform passengers? Um, I haven't really seen a whole lot in that regard. I think that most consumers would probably err on this side of wanting to see what the car actually knows. I know that that's really useful for me when I'm looking at the COMMAAI system. Um, I'll go back a couple slides. So looking at this system, it shows you where it thinks the lane lines are. It shows you where it thinks a potential collision is on your course or where a car is in front of you, basically. So you can see this little yellow arrow is telling you there's a car here. If we continue on this path, we'll intersect with their path. And then there's also the planned path, which is this white line in the middle showing um, and I don't think that the car necessarily needs to expose to you everything that is available, but there's definitely some useful cues so you can um, evaluate and have trust in what the car is doing. Because I've seen certain times on the comma system, it might start getting squirrely with the lane lines and lose where it's going, and that is signal to me that I can say, okay, I need to take over right now. Um, so looking at perception, this is the first section. Um, part of the problem. So imagine you get in your car. How do you start driving? Just think through that process for a second. You have to get in your car. You have to look around. You have to understand, okay, there's a curb to my left or there's a curb to my right. There's a car in front of me. There's not a car in front of me. I'm going to pull out of this parking lot. I need to go um, this direction in order to get out. There's a whole ton of things that you need to look at in order to determine what viable actions are, and you need to understand your surrounding. So you're looking for things like, are there cars around you? Are there pedestrians? Is there a obstruction in the road? Is someone getting too close to you? Where are the lane lines? Where's the traffic lights? Is there a curb somewhere? Is there a tree? You have to understand what is going on in the world, and so you record that with potentially LiDAR, camera, ultrasonic, radar, like I was saying. And so we'll take a second to look at what those sensors actually do. So the LiDAR is essentially shooting light in every direction, and then it's measuring a whole bunch of points in order to determine the distance to various different things. And so this is exceptionally accurate, but it's also exceptionally expensive. So most manufacturers have shied away from trying this approach because you can't put a $7,000 sensor on a $18,000 Honda Civic and expect to get any income back out of that necessarily. It just increases the cost of the car way too much. And so it's exceptionally accurate, and it's exceptionally useful, but it's also not in a current state where it can be utilized easily. And there's also several pitfalls with it where if, for example, let's say there's a plastic bag on the road. LiDAR is just simply saying, is there an object there to reflect back light? It can't necessarily say, okay, this is just a plastic bag, we don't need to worry about it, because all it sees is object. It doesn't know what object, it doesn't know, it just knows a distance. There is something in this distance in this spot. And so other methods are required in order to reason about, okay, this is just a plastic bag, we can drive over this, or this is a pedestrian, we don't want to hit this. And so that's LiDAR, and then radar is alternate variant of that. Basically, it has much worse precision, but it's cheaper to do. Similar pitfalls to LiDAR. And then there's ultrasonic sensors. This is kind of similar to if you've ever used like Raspberry Pi or Arduino or anything like that. They sell these cheap $15 sensors that basically just shoot out sound, and they just say how far away is the thing in front of me. And these are exceptionally simple, exceptionally reliable, and they're easy to put around your car. So if we look at like the Tesla diagram, they're basically showing there's a whole bunch of different points where you can just look directly out from the car, and you can say, is there anything close to us? And they're super cheap to deploy, so you can just put 12 of them, and it doesn't really tell you that much information, so it's not really overwhelming. What frequencies do LiDAR use? I don't really know that answer. I'm not sure. Is stereo used in any of these technologies for more precision, similar to having two eyes? I don't know the answer to that one either. I haven't looked into that. I would presume that there are stereo sensors. That's all I've ever seen in terms of ultrasonic, even in the cheapest little Raspberry Pi sensor. It's a stereo sensor. So I would assume, but I don't know the actual answer to that. And then the camera input is the one that a lot of people are banking on. So that's just a raw light. It's just a photograph like you would be used to taking with your phone or camera or whatever you're using. And there's some strong argument for this one being all that we really need in order to drive a car. Because if you think about it, in theory, a a car could be fit with a dash cam or something like that, and then that signal could be beamed to someone, and they put their VR headset on, and then they've got remote controls, and there's no latency and no anything else. In that scenario, in theory, a human could perfectly well drive just off of the camera signal, and they wouldn't crash, and they would be able to deal with things reasonably well. So the thought is the camera gives us all of the information we need. We just need to figure out how to actually use it. And so the difficulty there is we have the raw pixel values, but we don't know how far something is away. We don't know exactly what it is. There's a whole bunch of issues with camera where we have the information, but it's not as explicit in what it's telling us. With LiDAR, it's specifically saying there is an object 3 feet away at this angle. But when you're doing it with camera, you can say this area of pixels is red. It might be a car, it might be something else. It's hard to say. You need to be able to actually reason about that using the camera information, and that's where the neural networks and all of that stuff comes in. I see the chat popping away. I'm not sure if I'm going to be able to keep up with this. Do you think it's justified that Tesla Autopilot relies so heavily on camera input? Are there some dangerous limitations to only using ultrasonic plus camera input? So that's one of the things that I've heard some complaints about. So the people from COMMAAI have commented on the stuff from Tesla, basically saying your cameras have a certain amount of coverage and your ultrasonic sensors have a certain amount of coverage. The ultrasonic sensors have relatively limited range. And so the scenario that they laid out that was problematic is if an ultrasonic sensor has, for example, 60 feet worth of range, it can only tell an object is 60 feet behind it. If it's making the decision to merge lanes and the car to the right is going 30 miles per hour faster, it might not be able to see that, but in the amount of time it takes to merge, they've been collided in with because the ultrasonic sensor didn't have the range there. But in theory, the camera should have long enough range that it should be able to reason about that. So the approach that most people are banking on is eventually to get cameras alone to be able to do everything, because the other sensors are actually unreliable in some regard. Um, okay. Um, yeah, okay. I think that's all the questions. Ping me again if I miss something. And so another aspect of the perception, the first slide is all about actually understanding the world outside of you, and there's also understanding yourself. So you have to understand the vehicle state. So what I show on the right is a panel from the Comma Cabana, which is essentially a way to read the logs from past drives or live drives, depending on how you configure it. And so you can see it's recording all kinds of different values. So it's measuring how hard the gas is being pressed, what angle the steering wheel is at, are the lights on, are the lights off. There's all kinds of different diagnostics that are being shown here. And you need to understand what all of those are currently at while you're driving. You need to understand what speed you're going, how fast all your wheels are moving, what angle your steering wheel is at. Are you in the lane lines? You have to understand outside of yourself and also inside of yourself what's going on in order to be able to make decisions. Because, for example, if you're going at a high rate of speed, you can't just slam on the brakes and not have negative issues. So you need to understand what you're doing, because you might see that there's a car in front of you and you're going too fast and you're going to collide with them, but you also need to understand your car is moving fast, so that limits your actions. You might have to choose to swerve versus brake, for example, because that just isn't a viable option when your car is in a certain state. And so moving past perception, now that we actually understand what is going on in the world and the mechanics of the car, we have to go through various different levels of planning. So the most macro level is the route planning, and this is just sort of the stuff like Google Maps, where you say, okay, my goal is to get to the grocery store, for example. And so you have a starting point, you have an ending point, and then you have to figure out, okay, what roads do I actually have to take in order to get to that point? Maybe a road's closed, maybe there's a blockage, you have to do some rerouting. And you can potentially rely on stuff just like Google Maps, but you typically want to be doing that directly on the device because you won't always have online connectivity and there might be other issues there. What is reflected on Google Maps might not be 100% accurate right now, so you need to be able to adapt to the various different scenarios that can arise there. Um, should the car also understand what is going on inside? Um, if you mean like inside the cabin, I think in a limited sense, yes, because depending on the level of self-driving, um, you want to make sure that they're paying attention, but I don't think there's any need really um, to look at what the other people in the car are doing. So on the comma in the comma device, it's just facing the camera directly at the driver, and it's just looking at their face and saying basically, is their face looking towards the road? Are their eyes open? Do they look attentive? And I think that's really the extent of what you need. And even once you go beyond that, when you go to level 4 or level 5, that might be entirely unnecessary. Um, and so then beyond that, once you have a route, when you say, okay, I want to take the 30 miles this way and then I have to get off on this exit, then you have to actually build a plan. So you say, okay, I'm in this parking lot. I need to move out this way so I can go forward this way to get on this road. You have to plan all of that several steps ahead of time. And so this is what's shown in this bottom right picture. This is from the Udacity simulator. So Udacity is a site that has an online course that is focused on self-driving cars, and it's taught by one of the top guys in the field who revolutionized everything from the original DARPA challenge that was kind of just a research project trying to see can we traverse these difficult scenarios. Um, and so in this simulator, you can see that there's this green line, and on that green line, there's a whole bunch of waypoints. And so that's what we're talking about when we say path planning. You put a whole bunch of poses, and you say, okay, our car needs to be at this position, and it needs to be at X, Y, Z coordinate, and it needs to be this pitch and this yaw. Um, and it plans all of that ahead of time. And then on top of that, you have to say what what motion is required in order to make that series of poses possible. And so um, this kind of bleeds over into the area of controls. Um, but it's just you can't necessarily just directly say, okay, I need to translate left 1 block, forward 1 block, rotate 3 degrees. That's not that simple. You need to actually take actions several times per second, many times per second potentially. And so that's what the motion planning is doing. The more granular, how do we actually um, complete that plan, the path plan. And then there's the final issue of control. So we have a plan, we've got the route, we've got the path, we've got the motion we want to take. How do we actually turn that into movement of our vehicle? And so, like I was saying, you don't have it's not like you just say, okay, move forward on the x-axis. You have to actually turn that into controls that are applied to the vehicle. So you say, press the gas this much, turn the steering wheel this much, left or right. And you have to do that many times per second in order to um, live out the plan that the planner had laid out. And um, this is somewhat easy when you're doing it in a simulator or a vacuum, but it's significantly harder when you're doing it in the real world where there's potentially gravel on the road that reduces your traction, or your tires flat, or there's a hill, there's snow, there's all kinds of different environmental factors that you need to be able to address in order to make it do what you want. And this is kind of a very difficult area of robotics, that you need to be able to take the raw signals and the information you have and turn it into action in the real world. And so as for building models, this is where things get more interesting. So these companies have all taken very different approaches in order to get to somewhat similar solutions, actually. So we've got Tesla, who has all of their cars on the road, and they've got billions of miles recorded because they've had all of these cars that have been driving all over the place and capturing all of this camera data and ultrasonic data, um, and the internal state of the car, and saying, okay, when the person was in this scenario, they turned right, and when they were in this scenario, they turned slightly left, and they hit the gas. They're recording all kinds of stuff like this. And they have gotten so much data, billions of miles, that they're now able to hone in on the portions that they're bad at. So part of the problem is, like what I was saying, is 80% of my drive was probably highway, and I was going on the 15. There's so many people who go on the 15 and capture that same data and do that same route, and it's not very useful for the person in some backcountry area who's going down a windy road to have a model that has been dominated by driving up to 15 in a straight line. That's just not very useful. And so what they've figured out is they've built a data engine, is what they call it, where they address various different scenarios where the model is failing, and they're able to gather up a small hand-picked set of that specific scenario. So in this case, in the top right, what they're showing is they were having issues with occluded stop signs. So there's bushes in front of them that's blocking the full stop sign, so the model wasn't seeing them necessarily. And so what they did is they collected a whole bunch of them up manually, and then they train a model to say, look for this scenario. When that scenario occurs, they then deploy that model to all of the cars, and then all of the cars are scouting for that scenario. And then while they're driving around, they say, oh, there's a stop sign that has a branch in front of it. There's a stop sign that's behind a bush. And it grabs all of that data and then beams it up home. And now from that hand-picked set that had only maybe 1,000 occluded stop signs, they all of a sudden were able to quickly gather up 1,000,000. And then they can integrate that training data into their model, and now their model is able to address occluded stop signs or any number of various different scenarios. And in a recent talk, they were saying that they've basically done this for hundreds or thousands of edge cases, and that's one of the things that they're really heavily tackling. Is there's so many random scenarios that a car can get into, and they need to be able to address everything. And so they eventually want to get to that level 4 or level 5, and in order to get that, it needs to be successful always. And so there's all of these tiny things that they need to finally address. And then that's in contrast to Waymo, who only has a relatively small fleet of cars. They don't have the massive user base that Tesla has. And one of the ways that they've gotten around this limitation is they've driven around a whole lot, and they've gone and conquered specific geographic areas. So they've said, okay, we're going to go into Phoenix. We'll drive all around Phoenix. We'll get complete mastery of Phoenix. And hopefully they can capture that area, and if they can get proper operation within that, that's a good proof of concept. But on top of that, they've also built a really robust simulator that allows them to generate new scenarios and new problems for the model to address. So if you're interested, there's a whole bunch of videos on their simulation showing basically their car trying to address a car speeding behind them while they're trying to change lanes, and them getting out of the way of various different emergency scenarios. And it's kind of interesting to see how they've really thought through all these different scenarios beyond what they've just seen, because they have to kind of come up with these things because they don't have the same pool of knowledge that Tesla has. And then there's the COMMAAI approach, which is they originally started as sort of just a limited dash cam. And they said basically, we'll let you use this dash cam. It captures all of these cool metrics about your car. And while they were doing that, they were capturing all of the recordings of the state of the car and the video outside the front of the car. And then they were able to combine the two and say, okay, when we're in this scenario, the user seemed to turn the wheel at 3 degrees and they were putting the gas on this amount. And through that process, they essentially bootstrapped their own fleet from all of these people who were using their dash cam like device. And then eventually they were able to roll out a simple self-driving setup. And they've caught up in some regards because they've gotten millions of miles recorded from their systems because they're so cheap and they're able to fit in many different makes and models of cars. And on top of that, they have this interesting annotation system where you take your device, you put it in your car, you go drive somewhere, you drive around, and you say, okay, there were 16 different times where I had to intervene a little bit. I just had to correct the steering a little bit. I had to brake because someone merged in front of me. Um, and you go into their dashboard, and then it will show you basically every time you did some form of an override, and what they allow you to do within the dashboard is you can annotate them. So you can say, why did I need to do an override here? I needed to do an override because someone merged in front of me, or I need to do an override because the angle of steering it shows was not correct. There's all kinds of different stuff they have there, and you can add your own text there. So you're giving them feedback on their system as you're driving the car around and bringing it back and saying, okay, this was problematic. I need this fixed. And they learn over time as people give that feedback. Um, and then in terms of training models, we have to look at what does the model have as input, what is it trying to predict as output. So the input is all of that sensor data. What is the state of the car? What does it see around it? The camera, the LiDAR, the steering angle, all of that stuff is input. And then as output, potentially in a perfect world, you could just say, I'm just going to record everything, and then neural network, you just do your magic and you pick a steering angle and gas and brake amount, and you do everything. But the systems are not necessarily that complex at this point. So what people have done in order to make something like that work is they give the network lots of different subtasks to tell them about the world in order to act upon that. So one of those things would be like 3D bounding boxes of all of the cars around you. So if you can discern where all of the cars are around you with a camera, then you can do some simple planning based off of the bounding boxes that were provided. And on top of that, you can also do detection in terms of what are all of these objects. So in this example, this is from Tesla. They're finding the lane line, they're finding the road marking, they're looking at the crosswalk, they're looking where the curb is, they see the road signs, they see a cone, they say, okay, this is a static object, we don't really have to worry about this. It's not going to randomly move into the roadway. And they can look at the traffic light, they can say, is this red, green, blue? And so in current systems, it's doing a whole ton of reasoning and doing all of these outputs, and then people are building logic on top of what the neural network is able to discern from the world. But some people are arguing that down the road, we won't have to do that. We just essentially say, here's all of the input, here's all of the data we've ever had, figure it out on your own. And that's kind of a scary world because we have much less interpretability and understanding of what's going on in that scenario. In this scenario where people have defined tons of subtasks, it's very easy to see why a failure is occurring because, for example, if it sees a red light and you can see in the video it's a green light, that's something easy that you can correct down the line. You can say, okay, our traffic light detector was not good enough. But if you do everything end to end, it's much less opaque. You just have the signal of saying it decided to turn 3 degrees left and continue with the gas, but there's no explanation of why that occurred. But that is potentially an area where people are expanding into, is just the complete end-to-end approach. So looking at the ways that the various different companies are approaching this, most of them are looking at taking the various different inputs they have and stitching them in some way. So that's typically called sensor fusion. So you have your ultrasonic sensors and your camera sensors and your LiDAR, for example, and you have to piece all of that information together in some way to build that view of the world. And then you also have to do that across frames. So in this diagram, they show that we have these various different data sources, and then we also have a fusion layer, which is combining all of the information we have from all of these different data sources. And then on top of that, we also have to look at the temporal aspect of this. We're doing video, so we've got probably 30 plus frames per second. We're looking at multiple different things in sequence. It's important for us to be able to understand, okay, this cone is not going to move. This car is going to move. We have to be aware that they might make some action that puts them in our lane, and we need to be aware of what's moving and what's not. And you can only really capture that with the temporal aspect of things. And so with all of this information, it can then determine the moving objects, the road lines, the road edges, and then it can make this kind of bird's eye map of what's going on the road given those cameras. And then another task that some of the people have done, this is actually images from the Lyft Kaggle competition. They were showing LiDAR and how you try to determine the bounding boxes of the cars given LiDAR information. So the LiDAR information, if you remember, is light that's shot in all directions, and you just have the depths basically. And so you're trying to resolve where are the bounding boxes that encapsulate the cars from this point cloud information where you just have a whole bunch of points and distances. Something I've already talked a little bit about is the imitation learning. So this is the idea that in theory, all you really need to do is give the input that the driver would normally see to the model, and then you have to tell the model what action the driver took in that scenario. And in theory, that's enough for the model to learn how to drive. And so that's one of these core concepts where with enough data and enough scenarios and all of that, you should be able to get a fairly robust system just by saying, here's what a human sees, here's what a human does, match that. And the neural networks are actually pretty good at that, but it's not perfect. And so that's where a lot of these systems have started, and then they've built on these additional layers over time. And so with that imitation learning and then building on additional layers part, they need to put on these guardrails. And so the neural networks and the various different machine learning systems that are applying here need to be kept in check in some way. So you can't just go full throttle straight out of the parking lot. You can't be tapping the brake 37 times every second. You can't be going 75 on the freeway and just try to do a 90-degree turn. And so there's all of these guardrails that the companies have put in place, limiting the amount of torque that they can apply to the steering wheel, limiting the acceleration change they can apply, and various different safeguards that I've put in place to prevent the models from doing anything that can cause really rapid damage. And so one of the tenets from the COMMAAI system is making sure that if they are going to fail, they give you a warning, and if it's going to take an action, it does it in such a way that it's not going to be such a quick failure that you don't know, you don't have time to respond. So for example, if you're in a scenario like on the freeway, for example, it's not going to do a rapid merge that you can't react to. And on top of that, it needs to be able to be something that you can correct. So it can't make a decision that in a quarter second is going to cross you over a lane line, and it can't be with so much force that you can't overpower the steering wheel. Because a lot of these systems actually have enough torque that it can just jerk the steering wheel out of your hand, and you obviously don't want that. You want it something that you can correct if you have to. Um, and so here's a diagram. This is very complicated. It shows most of the stuff that we have discussed and maybe even more. And this is just kind of showing the flow. This is from a research system, and they're talking about the various different subcomponents. I kind of just grouped some of these together. So for example, you have a localizer, which is telling you where are you, what's your XYZ position, given all of this information. They can build a 2D mapper, which is saying basically we're operating in 2D space, but we can kind of flatten it to 2D and then just look at what's around us. Um, and then we have our motion planner and behavior selector that's saying, okay, what course of action do we actually do in order to reach our goal? And they also build in systems for obstacle avoidance and stuff like that. And so this is a relatively simple one, and the more complex ones like Tesla might have many more boxes and many more pieces that are trying to do lots of custom things. This is kind of just to show the complexity and the amount of custom work that goes into this. So for example, they're detecting road lines and traffic signs and traffic light states and pedestrians, and in the Tesla system they claim to be doing potentially hundreds plus of different things that they're detecting and trying to reason about. Um, and so that's all I have today. I guess we can open it up for questions if there are any at this point. I know there were some discussion. I don't know if I missed any specific questions. Feel free to unmute and chime in if you have one, or just put it in the chat. I believe that the neural network is directly determining the steering angle and the gas and the brake. That's my belief. I haven't looked closely enough to know for certain though. There's the question is what is the annual self-driving car competition? So the famous one is the DARPA Grand Challenge, and they've had that kind of random years. They aren't still running that annually, but that was kind of a challenge that DARPA put out. That was it was originally the challenge was to drive through some desert terrain, and people eventually conquered that. And then after that, they did a challenge that was doing urban terrain, so actually trying to navigate some simulated city streets and stuff like that. And I'm sure there still exists various different challenges, but not to that scale. That was kind of the big thing that kicked a lot of this stuff off. What value did I find in the Udacity program compared to a course like self-driving cars on Coursera or courses from Udemy? I did not complete the entire Udacity course, so I can only talk to probably the beginning half of it. Um, and I've also taken courses on Coursera, but not necessarily that specific one, so I can't exactly speak to that. But I can tell you that the Udacity course is infinitely higher quality than almost anything around, but it's also $600 a month or something like that. Um, and so I would say it's definitely worth it if that is a specific area that you're interested in because they teach you everything from ground zero basically. Um, all of the C++ code and the various different tools that you need in order to become a self-driving car engineer. And I assume that Coursera and Udemy would have something that at least touches on this stuff, but I don't think it would be nearly as complete. And the guy who does the Udacity program, um, Sebastian, I don't know if his last name is Thurn or Thrun, um, but he was one of the original competitors in the various DARPA challenges, and he's just a leader in the field. So I think it's worth listening to his course at least. Is it actually 1:30 p.m.? I magically timed things correctly.